Good morning and welcome to our second of Purdue INMAX July 2020 webinar series. My name is Mike Ursum and I'll be introducing today's session as well as our speakers. This webinar was hosted from Purdue's Intelligent Manufacturing Testbed Facility in West Lafayette, Indiana, and was developed in collaboration with Purdue's College of Engineering, Purdue Polytechnic Institute, and the Wabash Heartland Innovation Network, or WIN, which is a regional initiative created through the generosity of the Lilly Foundation in cooperation with communities and businesses all across Northwest Central Indiana. A few words about INMAC. INMAC was created to strengthen Indiana's manufacturing ecosystem by enhancing the relationship between Industry 4.0, tool and skill set adoption, and next generation workforce readiness. We do so through three core program areas. First, education, workforce, and development, in which we invigorate talent pipelines in a highly accessible manner through a range of K-12 and incumbent workforce programs with our partners all across the state. Additionally, we provide integration and innovation services in which we work with companies at their sites all across Indiana to implement modernization projects. More recently, we've launched the Intelligent Manufacturing Testbed, which is a research center that investigates ways for all manufacturers, regardless of their size, to overcome barriers to achieve Industry 4.0 in ways that work for them. A few more words about our Testbed Center. We conduct a range of research in smart manufacturing and the digital twin across all levels of the manufacturing enterprise. This center provides a platform for industry to develop and validate technologies to integrate and manage data streams across the product lifecycle and the entire value chain. The center includes a fantastic array of production assets, including lightweight composites manufacture, injection molding, subtractive machining, subassembly, and others. We have rapid prototyping capabilities, both through integrated design and software simulation suites, and some additive manufacturer assets as well. To this, we have metrology capabilities that provides rapid validation both at the manufacturing cell and offline. And through all this equipment, we manufacture real products. In doing so, we leverage IoT technologies and real-time information streams to study and showcase ways companies can achieve Industry 4.0. As soon as the restrictions tied to COVID-19 ease, we look forward to seeing each and every one of you here, meeting our students and working with their faculty at an in-person seminar or workshop. This workshop series is the second of three. Next week, we have a session on cost optimization in robotics and co-robotics driven production. We certainly hope that you can join us then as well. These sessions were created by a diverse range of faculty experts that touch a number of very interesting fields. And today's session will be addressing emerging metrology materials and model-based techniques. In it, we'll provide a perspective of how the flow of product and process information can be leveraged and understood throughout a product lifecycle. Additionally, we'll provide some insights on how data can be harnessed within the digital thread to improve the ability for an organization to make decisions. The format today, participants will remain muted. There will be about a 45-minute discussion followed by a Q&A session. Moderators will address those questions as they come in through Zoom's Q&A tool. And after the session, there'll be a participant survey. Please consider responding to that survey when you receive information. We do value your feedback, and we'll use those insights as we prepare for future sessions. Without further delay, our presenters today include Dr. Nate Hartman. Dr. Hartman has a number of active testbed projects touching the digital bill of material, digital bill of process, and digital work instructions, as well as the use and development of digital twins in assembly. Joining Dr. Hartman is Dr. Michael Sangid. Michael Sangid conducts a number of projects within our testbed facility, including the use of model-based feature information networks, as well as resolving designer intentions to actual product variability in digital twinning. Without any further delay, I'll pass it over to Dr. Nate Hartman.
All right, thanks, Mike. Good morning, everyone. My name is Nate Hartman. That way you can try to associate a name with a voice. Mike Sangid and I are going to present these back and forth a little bit. There will be a demonstration towards the middle of the presentation, and then we will wrap up with some final points and comments to review, and then we'll open up for questions. You'll see a slide like this periodically through the workshop just to kind of give a sense of where we are in the overall scope of the presentation. This is also it's sort of an entry point or a whet the appetite kind of a workshop. We're planning a more advanced, more in-depth version of these workshops once we are able to bring people back to campus. So with that, let's go ahead and get started into the introduction. Mike, if you would go ahead and advance. One of the things that really impacts this particular topic of metrology and model-based methods is this digital transformation that has happened from moving towards paper-based or analog methods towards the idea of digital. And this figure here, there's a reference to it in small text down at the bottom, but it's been adapted from its original use. And the key point about this particular figure is if you look at, for example, how music or how photography has evolved over time, obviously it has not only changed its data form, but it's also changed the platform in which the information gets distributed. And that's really the key point here in this particular slide, is that we find ourselves in manufacturing moving from this idea of physical and local to digital and to the cloud. And whether it's as a platform, whether it's as a dissemination mechanism, or whether it's simply how we exchange information, this is certainly changing the way companies are in fact doing business. And in many cases, the product becomes a service, or the product becomes a platform rather than just a discrete object that people purchase and use. And related to that, go ahead, next slide, please. Related to that is this idea of the model-based definition. And from a very basic level, the intention here is to be able to define a more intelligent artifact. Historically, people have used technical drawings for many different things. People have even used CAD models with notations in them for many different things. But most recently, as we want a more integrated process and a more integrated thread of information through the organization and through the life cycle of the product, we're finding that the current artifacts we use for communication, even if it is a three-dimensional model that you see here with shape definition, how we get to the behavioral and contextual information that surrounds a product. And that is often important to know when it comes to metrology and when it comes to the inspection and validation, even certification of a product. We need a much more intelligent, much more robust data stream that follows this communication thread through an organization. We do really well at, comparatively speaking, with human-to-human communication. However, if we're going to get to the other end of the spectrum, machine-to-machine communication, we need to have a much more rich information thread. And so this theme right here is something that's going to pervade this entire presentation. Next slide, please.
Okay, so hello everybody. I'm your other instructor today. My name is Mike Sandu, and Nate and I will be kind of jumping back and forth throughout the rest of this presentation. And as Nate talked about, as we start to carry information along with just the shape and geometry of a part, to really get to this next level of context, we need to know something about how the part, what the part is made from. So what is the underpinning material here? So when we view materials, we have such a thing as pedigree, where all materials are not the same. Actually, each material starts to be very, very unique based off its prior history, its composition, and really the processing route that it took to get here. So you may see from many standpoints, on the left is a specification sheet for a material. This says the composition range and some of the individual processing routes to achieve that material. And in the lower right-hand corner, you'll see as well, just for any given material, here's aluminum 7050, you'll have different forms and conditions based off of how it was heat treated, what form this comes in, whether it's a forging, a plate, or a sheet, as well as any types of manufacturing routes that this material will take. Why this is important, if you look in the view in the middle here, this is really what a material scientist sees the material. So we start to see all the individual grains. Here you can see the colors representing orientations, and you can see a distribution of sizes and shapes of these grains. We start to care about the materials at this scale. Not everybody does, but it's really the manufacturing route that tells us information about how this grain structure is looking. We call this the microstructure. And why we start to care about this is this really gives us the behavioral information of that part. So how this part, well, the material and so far the part will behave in its environment. So from this, we have this standard triangle where from any given processing route, we get a structure of the material that starts to inform the properties of the material, that starts to inform the performance of this overall part. And it's this connectivity, it's this history here, where if we want to keep track of the individual performance of the part, we have to know how it was manufactured. And with that manufacturing route, we need to know how this material evolved into its microstructure and what performance or what properties it can undertake. So this is the level of detail that we have to track for every part, going from processing route to microstructure to invoke the overall performance of that part. So next, we're going to talk about some of the related technologies that will start to inform the information network as follows.
Thanks, Mike. As Mike mentioned, one of the important elements in this discussion is obviously metrology and how we measure, and in a lot of cases, what we measure when it comes to understanding whether we have made our parts to their appropriate specifications and to fulfill their particular functions. And when we do that, historically, we would often just simply use things like limit dimensions, and then came along geometric dimensioning and tolerancing, and that's been the state of the art in some respects for a long time. And then we began to have increasingly sophisticated measurement devices, and we'll get into some of those in a moment. But the idea has always been, and for those of you who work in a quality role or have maybe either now or in the past, you'll recall that there are still a certain amount of assumptions that are made about whether or not the parts are accurate and whether or not they fulfill their specifications. And for a long, long time, we would often make assumptions about the materials that we had and the processes that influenced them based on rules of thumb or heuristics or past experience. And while that may have worked for a while, more recent advances in metrology and more recent advances in material modeling have given us an ability to more accurately understand things like process control and dimensional control, and how we're able to quantify the variability that we have in our processes. And we all know that tolerances are decided based on a number of different things, all the way from the machine operator to the tool to just functional distributions. However, one of the things that has always been difficult to account for is the characteristics of the material. And again, as Mike mentioned in the previous slides, that's been the focus of our efforts, which is to make a more intelligent measuring and validating mechanism. Go ahead to the next slide, please.
Okay, so when we go into characterizing the material, there's not just one type of characterization. Characterization is pervasive across the different length scales of the material. So all the way down from the far left, you'll see where we start to probe individual atoms, and we start to quantify the structure, placement, and quantity of individual atoms. We can start to look at secondary phases at the nano and micro scale. And then really even how these starts to form individual grains, much like a piece of wood has a grain structure, most metals have a grain structure as well. Around the millimeter scale, we start to look at having individual coupons and testing those coupons for a variety of mechanical behavior. And we start to then make those coupons into the shape that start to mimic the features on our components. We might end up testing an individual component, or we might end up testing a full-scale assembly. Regardless of if we're testing the material at various length scales, testing coupons, components, or assemblies, we need to be able to track that information. And we need to be able to track that information intelligently so we can learn from that information. We can use it in our analysis, and then we can also use this in our version 2.0 designs. So how are we going to use this for the next design iteration? Really, in all of these aspects, all of this material characterization at these various length scales really start to inform the mechanical properties of that material. So in the lower right, we show mechanical properties, and at these various length scales, they might have different effects in these sorts of mechanical properties like stiffness, strength, elasticity, plastic behavior, even weldability or hardness, or some long time dependent behavior like creep or fatigue, or just a manufacturability. So this could be weldability, formability, castability. So it's all of this richness that goes into the material that we want to really be able to harness and use this within the product management structure of what we're saying will be essentially Industry 4.0.
So where does some of this information begin from? This slide, I suspect, won't be new to many of you. However, maybe a couple of things that I'm going to say about it might be new to you, and that is one of the things that's important as we think about how we build information to support this concept of a digital thread that supports the life cycle of a product is to think about how we create the representation of the product to begin with. And for those of you who spent any part of your career working with technical drawings, you'll recall that there was a lot of information on the drawing that was not necessarily the geometry of the object. And while we lacked, in some cases with a drawing in terms of geometric precision, we made up for in additional information that provided background and context and other sorts of information cues to the reader about the specific details of that product now, or that component. Now today, we're almost in the reverse situation at times where we have a very geometrically precise representation of the object, yet at times we have a very disconnected thread of information that is attached to that model. And so part of the work that Mike and I have been doing here, and one of the reasons for wanting to do this presentation and for crafting it the way that we did, is to try to help people understand how to begin to connect both the geometric and the non-geometric kinds of information, and more specifically with the context of metrology and how we measure and validate these particular components. Go ahead, next slide, please.
Okay, so once we have the CAD level design, the next step usually is some form of analysis. So commonly, one of the pervasive usage of this analysis is the finite element method. And really what we do is we take a three-dimensional complex shape, usually from the CAD model itself, and we discretize this into small individual elements. So across those elements, we start to inform constituent relationships of how the material behaves. This could be simple elasticity, it could be heat transfer, it could be more complex plasticity. We look at how the part would behave in terms of applying, either fixing the displacement or applying forces known as tractions on a lot of the individual surfaces or boundaries. We call these the boundary conditions. And then we apply some sort of loading, and this could be a thermal load, it could be a mechanical load. So this finite element method is really universal, depending on the types of analysis you want to do. So the nice thing about this computational method is it plugs through all of the math, keeping track of the compatibility where two elements can't overlap with each other. And if they break apart, there has to be added physics there in terms of why a new surface is created. At the same time, it's keeping track of force equilibrium, making sure that we satisfy Newton's second law of forces across two elements. Then we can output any quantity of interest we want, and you may have seen a lot of these sorts of spatial maps where we have color contour plots, and this could be of the amount of displacement across the part, could be strain, could be stress, it could be temperature. And usually the nomenclature is anything in blue is low values, anything in red is high values. So those regions in red, the hot spots, are the regions that we really start to care about as having high quantities, and those could be more prone to failure. So these are the types of analysis that we do to make sure that our parts can withstand what they might see in the field. So the question remains, how do we actually get that type of information about how the material behaves? So I previously said that the pedigree of the material really starts to matter. Its form, its history, its, and processing routes. So rather than get this purely by testing, there is a growing field called integrated computational materials engineering, where we use models to replicate and simulate every process from the composition of the material to all of the steps that go through the manufacturing route. And from following all of these steps, we can start to recreate what the mechanical behavior of this material will be. Why this is really valuable is we're no longer just picking out individual values from tables, or we're not reliant on solely doing experimentation to understand what the mechanical behavior is of a material. We can treat the material as a design variable and start to iterate and optimize the manufacturing route and the material simultaneously to make sure that the material performs as we want it to within the design. So this gives us additional degrees of freedom, additional treatment of the material as a dynamic variable to really optimize the use of the material within a given component.
Thanks, Mike. And so one of the things that we have to be able to do in a situation like this, which is to say, if we're going to use information in the way that Mike was just describing, particularly in order to inform decisions that are made either during design or during production or even during inspection and validation, we have to have a way to accurately capture and understand what the resulting as produced or as manufactured object is. And so one of the things that has historically evolved is this idea of a coordinate measuring machine. I suspect that most of you, if not all of you on the call, have seen or used or at least been around this kind of a machine. It allows us to capture information about the resulting shape of the object, and it allows us to do that with a fairly high degree of accuracy and precision. However, the challenge with a CMM is that it's slow, relatively speaking. You know, you have to program it, you have to put the part on there, you have to run the process, and then you get the results. Now, they still have their uses by all means, and I'm certainly not saying that we should get rid of them. However, you have to take the pros and the cons with that particular approach. Another thing that's been happening more recently has been the use of laser scanning. And the nice thing about these types of technologies is they tend to be smaller, they tend to be more portable, they tend to be a little bit easier to use, and often they can be less expensive, although not always, but often they can be. These allow us high-resolution scans of the exterior features of the object. Now, this won't replace other more advanced techniques that allow you to look internally, but they will in fact get a high-resolution image by way of a point cloud of the external features of the object. And so just as a bit of a recap up to this point, we started by talking about geometry. We started then talking about the assignment of material and behavioral information to it. And just now this slide begins to outline how we capture the resultant shape from the manufacturing process. And as we continue to go further in the presentation, you'll begin to see how we begin to link those items together. Let's go ahead to the next slide, please. One of the ways we begin to link these two areas together is by way of relevant data standards and formats. The reason this topic is important in this conversation is because when we had, let me say it from this perspective with a bit of history, and that is historically when we did many things by way of a paper-based format or a paper-based process, it was very easy for us to create and consume that information. Human beings obviously readily were able to see and look at paper-based information. We did not have to worry about paper 2.0. That was typically not a problem. But yet when things began to become digital, we had to begin to be concerned with, is the information clear? Is the information concise? Is it unambiguous? Will it transfer from one version of a file or one version of a software to another? Will a particular machine from one vendor actually be able to read the information from a different vendor? And so, and there are a host of other challenges and considerations and opportunities, to be fair, with this kind of an approach. But this slide is meant to summarize some of the things that we encounter when we talk about exchanging information across the life cycle. And obviously our presentation today deals particularly with the categories around product definition and quality and inspection, but I suspect many of you have probably encountered most, if not all, of the kinds of information that we've listed here on this particular slide. But the importance of relevant data standards and formats is that without these, we end up not being able to communicate in a digital thread that is connected across the life cycle. Next slide, please.
Okay, so as we start to talk about having information flow across the life cycle, this brings us to a major aspect where Nate and I have worked over the last several years in creating a model-based feature information network. So this is how you include all the metadata within your product and then have it flow throughout the product lifecycle aspect management here. So within our design, we have model-based definition. So this is the semantic product and manufacturing information that Nate's talked about, including the material definition. From the analysis, we link this to the finite element models that we had previously talked about. We link all of the manufacturing process plan to the MFIN, so we know all of the steps that it took to make this material. Then from the inspection, we look at the geometric quality. So planning the data within the inspection plan the data from the model-based definition. So this could be coordinate measurement machine or laser scanning that Nate previously talked about. And then ultimately how the part is behaving in the field. So this can be maintenance, repair, and overhaul, and the overall service information of how that information or how that part behaves in the field, how many times it's inspected and repaired, and then ultimately to the overall end of use life and when it's ultimately retired. The important aspect here is closing the loop. So going from design analysis, manufacturing, inspection, to MRO, but back to the design. So when you're designing the next iteration of this part, you're learning from all of its previous experience that part went through. Commonly, what we rely on is expertise from the most senior engineers or manufacturers or designers within a company. But this really gives us an opportunity to harness all the information from previous generations to use this to inform the next design iteration to really start to optimize our parts. So next, we're going to look at some of the overall process and step you through what we think that the process could be in moving towards an Industry 4.0.
Thanks, Mike. So with that, this next section of the presentation, we're going to paint the large picture here with this particular slide, and then Mike is going to walk us through a demonstration of how something like the MFIN would work and how that can be advantageous. But if you think about, for example, the part in the upper left, what is it that we do in order to inspect something or to make a determination about whether what has been produced is good and whether it fits with the specifications for which it was intended? So if you think about the numbered boxes, we programmatically generate and evaluate what our measurement plan is. Now, for some companies, there's a little bit of a manual process here for data entry. For some, it's more automated. But generally speaking, we create and arrive at our measurement plan. We do our analysis to determine whether or not the uncertainty, the variance, the tolerance, people use different names for this, although I'm going to try to stick with the terminology of uncertainty at this point. Is that acceptable? If it's not, then we have to go back and redevelop our program. But if so, then we move on to our measuring stage. Now, whether it's a CMM or whether it's a laser scanner or whether it's some other sort of measuring device, this may vary a little bit. But stage number 3 is we move on to our measuring stage. And you'll notice that you'll see something there called QIF. For those of you that might be familiar with this, it's the Quality Information Framework. It's basically the result of a partnership between NIST and several hardware and software technology vendors, as well as some of the industry people that have participated in this to provide background information and some specifications or desired deliverables. But the QIF is a format. It is something that is being standardized by ISO, and it's meant to exchange information between the design, the production, and the metrology communities. And so after we do our measurement, you'll see we move around in the green boxes there. So step number 4, we gather our measurement results. And at that point in time, you'll see that there's a diagonal line coming over where we're communicating with this idea of a CAD or a neutral file interface. And so this is where we begin to see the digital thread, if you will, continue to close some of the holes that may have traditionally been in a paper-based or more manual-based communication process. And that moves us on to step number 5, where there's a comparison made between the as-designed and the as-made version of the object. Now, historically, this would have been done purely with dimensional information, comparing what was produced to what was designed. And the challenge there, if referring back to some of the previous slides, is that we would have historically been focused on just the geometric dimensional information. Were the sizes correct? Were the positions correct? However, with this framework that's been developed, we have an ability to also begin looking at materials and the ability to convey the effects of those materials on the actual finished object, more specifically at a feature level, which is often the important level of detail when you're doing inspection to determine functionality. And then ultimately the results from that inspection plan are mapped back into the model, ideally in some kind of a neutral file format so that it can be further communicated throughout the life cycle. So with that, that's a high-level overview. And on the next slide, or in the next section of the presentation, Mike is going to walk you through a demonstration of how this works with the MFIN technology that was developed as part of this project. So take it away, Mike.
Okay, so now I'm going to go over a piece of work that Nate and I worked on together over the last 5 years. And this was really funded through MXD, which is the Manufacturing USA Institute out of Chicago. So the two people that really did the heavy lifting here and that are responsible for the bulk of this framework are two grad students. So Saikaran Gopalkrishnan and Kevin Del Rey. So I want to give a lot of credit to them for the framework that you're about to see. So the model-based feature identification network, or feature information network, we call this MFIN. It starts with the CAD model. So from the CAD model, we have the material notes, and this could be the product and manufacturing information. It could also include tolerances. It can really include all of those types of notes that Nate talked about typically being on drawings. So the next thing we need to do is convert this to a neutral derivative file. And for the purpose of this MFIN, we use XML. So with this, we can start to identify unique parts. So you can imagine as we start to produce, here is a blisk, a bladed disc. We might produce 50 of these. So we'll have a unique identifier for each part. As a second level of fidelity, we also have a unique identifier for each feature. So this could be a geometric feature or it could be a region. So what those unique identifiers allow us to do is track individual geometric features that might be tied to specific material information, or it could be tied to specific material notes or tolerances for that matter. So next, we save this into a database. And this database could be on a single computer and in a file. It could be on a shared network drive, or it could be even on the cloud. And last, we connect this via materials database. And we've done this in two forms. We've looked at commercial tools like MSC Material Center, and we've also looked at Grant Anamati. And we've shown that we can link specific materials to a part, or even specific feature information to a part, especially in the case where we start to have gradients of material information based off how this type of part is formed. So next, I'm going to show you a very simplified demonstration where we look at two materials, and we kind of take geometry out of this and look at just two simplistic blocks. So we have an outer copper material, and this could even be a coating, with on top of a stainless steel block. So this is going to be a video, and to kind of make up for a little bit of time here, I'm going to skip ahead. But our first step is creating the CAD model. With the CAD model here, you see the two blocks that I'm showing. And these are two features. One is copper, and the other is stainless steel. So they're shown up as notes or material labels here. And we apply the product and manufacturing information, and we as notes. So then we have to convert to derivative files, and we're going to do this two ways. So the first is we're going to output a step file. And this step file we're going to be using for our finite element analysis that comes up next. And while that exports, our next step here is that we're going to export the QIF XML derivative file. So this is what we're going to be used to store within our MFIN framework. So as that saves, I'm going to skip ahead. If we open this up within MVD video, it allows us to view the MFIN model, including all of the feature IDs and all of the product manufacturing information. So here are some of the notes that it saves. The next thing that we can start to look at is to link this to our materials information. So here we start to open this up, and we can link both the steel and the copper to specific materials information. Here we're showing from AS standards. And we can link both sets of materials to the databases that we have at our disposal. So here we're just looking at standard elastic and physical properties that we're going to be using downstream in our finite element framework. So this allows us to capture and to really accumulate all of the pedigree information of the model. And lastly, what we'll do is we'll output that XML framework to a file that we can then read into our finite element analysis. So this is a lot of details and a lot of information, but in simpler terms, what we're doing is starting with a CAD model. We're linking this with materials information, and we're doing this at a feature level across the part. And this starts to build or inform our MFIN framework. We can then use the MFIN within our next step, which is analysis, so to inform our finite element model. And from the finite element model, we get our finite element results, and I'll show you that on the next slide. And then we save those finite element results back within the MFIN framework. So we are capturing geometry, material, structural analysis, all within the same information flow. So the next thing that I'm going to show is a very quick overview of our finite element framework. So we've shown this, we're showing this in both MSC Patran here. We've also built this within another commercial tool, Abacus. So this MFIN framework, it should be, for the most part, working with commercial tools, but it's software agnostic. So our first step here, you'll notice that we have an MFIN tool built right into, that we developed and built right into MSC Patran. So we click on this, and we first want to import our previous geometric model that we previously showed. So for the purposes of kind of setting this up, I'm going to step through a few here. So you see our geometric model, and we have the copper coating on top of the stainless steel block. We import the material information, and from the material information, we import that's saved within the MFIN, and you can see here the elastic and physical properties. And next, this is essentially where it becomes a little bit like a cooking show. We're not going to show you all of the finite element analysis, but the next thing that somebody would do is go through, build the mesh, apply the boundary conditions, apply loading, and then from there we can start to see the results. So here I'm going to skip right to the results. So this starts to show you the generated results, and we can look at the stress across the copper and the stainless steel block. And the important thing that I want to note here is then we can save all of these results as CSV file, and we can embed them back within the MFIN framework. So from this, the analysis follows our information flow within the same digital thread of this material. So this is just a high-level view here, where we start to look at forming different functions. And from those different functions, we have H5 files that output the results from the finite element information, a BTF file that's a body definition file, and then as well, you can see here we have feature-specific results. So we can look at the stress within a specific feature as defined within the component and save that back under the feature information. So we can look if there is something that we're tracking that goes array at that specific feature, we can look at the stress, and we can always update that stress to take into account a specific anomaly of building that feature. Next, and I think for the purposes of time, I'm going to really skip the demo here, but I'll just say broadly, previously we showed you a specific feature on a component. Here, let's look at an assembly. So this is a bike crank assembly made up of 3 parts. And with those 3 parts, we can develop those parts, and we can do the same thing. Start with a CAD model, link this to a materials database, do a finite element analysis, and then produce the part. The thing that I want to concentrate on this example is if we look at just the left crank arm, and this is going to be bikes where we make many of them. Here we show 50 left crank arms. If we manufacture all of those 50 left crank arms, we could do CMM on each of those. And I'm going to skip the purpose of the video here in the demonstration and just skip right to the results. Now we can start to really harness the information of the CMM of those 50 different crank arms to look at control charts and look at the tolerance limits of each of those 50 control arms. So in the previous example, I showed tracking a specific part and looking at features and making sure that we capture the specific features within the part. Here we're looking at building an array of 50 parts and then tracking the tolerance issues, and this could be used for quality as well as calibration of our machine. Are these within control limits? And this is the power of really this digital thread aspect of the model-based feature information network that we've developed. Okay, so with this, let me switch back over to the other presentation. And you should be able to see this. Now we're looking at possible business impacts. And from this, Nate is going to talk about how all of this is really important.
Thanks, Mike. So one of the things that is important to remember in this particular presentation is that we have a situation where there does need to be a certain amount of thought and consideration given to the use of these particular technologies. And one of the things that is important is that there are benefits and challenges that go along with this. Ideally, this can compress overall amounts of time. Ideally, this approach can remove error. We can arguably reduce our quality escapes and make products or parts correctly the first time. However, this approach does rely on a certain amount of interoperability and the ability to capture proper information in the right format to be able to be interpreted and read by items that are farther downstream. And so, okay, so as I was saying before, one of the things we have to do from a business consideration perspective is install and configure a proper infrastructure. And so whatever hardware, software, and information flows that your company chooses, you need to make sure that the software and hardware and information tools are talking to each other, which is one of the reasons why we relied on the use of neutral file formats, whether that be STEP or QIF. It gave us the best opportunity to be able to have as much interoperability as possible as we were moving information from one stage to another. And ultimately, getting people trained on whatever portions of that digital thread that they're on is necessary. And so with that, I'm going to pass the presentation back to Mike. Mike, go ahead and go to the next slide, please. And Mike's going to walk us through a bit of a use case on capturing residuals using that.
Okay, so I'll keep this, I guess, really short. Previously, we talked about moving up the level of information from drawings to CAD models to looking at how this may result in behavior. And here we show an element model to how this would start to behave and mimic how this would start to behave in application. So in an engine and across really the whole life cycle. So now if we look at one of these components, and this is a turbine disc, we can look at what goes into forming that disc. And usually that's done by a forging process. And there are plenty of process modeling capabilities here where we look at simulating the forging process and looking at how internal stresses are really developed from the manufacturing process. And we call this the residual stress. A lot of times what happens here is we validate these by putting thermocouples within the material and really monitoring the results of those, or the temperature readings on those thermocouples. Why this starts to matter is within this framework of the digital twin of these components, we can look at slight deviations from the forging process. So this can be deviations in the process from part to part. It could even be variability in our simulated practices. So here we show 4 different turbine discs where each of these could be a separate serial number. And from this, we're seeing small changes in the residual stress at two locations within the cross-section of this turbine disk. If we start to forward propagate what those small differences in residual stresses are going to be. So the residual stresses here are going from 100 minus 113 in compression to small deviations minus 14 also in compression. So not extremely large differences in residual stress. But if we start to propagate that into the damage tolerance behavior of this material, so this is if we have a crack at one of these two locations, how long would it take that crack to grow into an unstable length that's prone to failure? And we can see based off tracking that difference in residual stress, we might get anywhere between 2.5 million cycles to failure to 3 million cycles to failure. So imagine this, if each of those cycles is one flight of that turbine disk, based off those small deviations in manufacturing route, some of those parts could last 2.5 million flights. Some of them could last 3 million flights. This is the type of information we want to track and keep going along our whole life cycle, so we know when to inspect, repair, and ultimately retire these sorts of parts.
And so with that, what does that mean for companies in the long term? Is really a new business model. This idea of using data and analytics, of using standard interfaces and formats to leverage and to drive that digital product definition. And hopefully, up to this point in the presentation, you've realized that what Mike and I are advocating for and suggesting is that we're moving, we have to move beyond just the geometry definition of an object and how we use that across the life cycle, but to a much more integrated thread of information. And on the right of the slide are some things to think about of what this new business model and what this new future can look like as it relates to product data. And it won't simply be a business model based on producing a particular product anymore, but can you provide support? Can you provide traceability? Can you provide a future-looking service to a customer? And much of this is based on digital data that comes from not just the design process, but also the production and analyses processes as well. Go ahead to the next slide. And so finally, we have a summary here of just a couple final points. Mike, go ahead and jump to the next one. So what might an information integration look like? Well, over the course of an enterprise, the important point here is that information access provides us the opportunity to make better business decisions in a more timely fashion. And that is increasingly important as product complexity and volume continues to grow. Next slide, please.
And within an aspect of this digital thread, we can also look at the digital twin. So we're going to treat this as two separate but beneficial value propositions. The first is, as we're starting to increase the complexity of the part, this means that the physical prototyping, the manufacturing trials, the amount of testing of those parts just increase. So dealing with that level of complexity leads to longer and longer development cycles, where lots of the costs are baked into this part really before we start to develop the first physical prototype. The more information that we can start to capture and simulate upfront, so moving this to a digital environment, will reduce the development cycle and make sure that we're essentially right the first time. The second aspect of this is what we start to show on the right. So the second main benefit is that when we start to forecast the performance of a component or an assembly, we're forecasting this based off our prior information or prior knowledge of how that's going to behave in the field. As we talked about, as the parts are produced, if we keep track of all the manufacturing processes, if we keep track of all the material evolution, we'll have a more exact understanding of the material condition, if we start to track all of the loads that happen in the field, we can update our analysis and essentially reduce the uncertainty of our predictions or our future predictions. So this is the type of information where we keep track and rigorously update our models. We can essentially reduce any level of uncertainty into future performance. So with this, we are happy to conclude here and take any questions that you might have. And then just as a shout out, next week we will have a future or our next workshop. So it's the same time next Wednesday, where we looked at cost optimization robotics and co-robotic driven production. So the floor is really now open for questions.
Thank you, Michael. Thank you, Nate, for the great presentation. We'll watch the Q&A board for a few questions to come in, and there are a couple questions that I'll ask the presenters just to get things started. So linking materials representations to the geometric definition of a model seems complex. Is there a way that this can be made more straightforward for adaption?
Yeah, so most of at least the value proposition for this type of question and methodology is what led us to make and develop the model-based feature identification network. So it's a way of tracking all of the types of information that goes in from the material, the process, really the field usage, and have it flow in a streamless way to be able to build those connections and those linkages.
Thank you. Another question here is, what are some of the biggest hurdles for implementing these techniques in the design and product qualification process?
Thanks, Mike. I'll go ahead and comment on that one. One of the big hurdles is internally to an organization creating standard, for lack of a better word, methods for how geometry gets created and stored. Many companies have some of these kinds of standards, some of these kinds of processes. They may not be complete, or they may not be comprehensive. So one of the immediate things that a company could do is begin to standardize, in whatever way that means for them, a consistent way for creating geometry, because that'll give us then consistent elements to link to from a materials and from an analysis and from an inspection perspective.
Yeah, and if I could piggyback off that, I would say another major hurdle here is, as with any sort of industry base or any sort of issue, is really cultural. It's the aspect of wanting to start to develop and embrace new techniques, and usually we don't know really the return on investment until after we've started down this path. We know that there's value added here, but we don't know essentially what the bottom line is until we start to have some data coming in. And that's always the cultural aspect of looking to adopt, change the current practices and adopt new techniques when we're not forced to, but really we see the market pulling us in that direction.
Great, thank you. We have a question from a participant. Are you currently working on any project for machine digital twins, more specifically focusing on manufacturing shop floor instead of the customer, as was demonstrated in the turbine example?
So I think Mike and I probably could say something about this one. Let me offer this comment first, and that is, generally speaking, we are considering this idea of a machine digital twin. It's obviously, in our mind, I think it's the next step after we begun to consistently be able to define the analysis and the metrology equivalent to the digital twin, because one of the elements that potentially comes in during the behavioral and contextual definition of the object is what happens actually during the machine process at the machining level. One of our research colleagues whose picture was on one of the early slides, his name is Martin June. Martin has done some work in that space as well, and Mike is also doing some work in that space. So Mike, go ahead and throw in here from your perspective.
Yeah, so I think there are several aspects here. Is one, if we start to look at the quality aspect, and we showed the simple example of keep on measuring parts and understanding if our calibration needs to be is drifting in a unsafe manner. Really, the low-hanging fruit here is on tool life. And if we start to monitor really when tools need to be replaced within a machining operation. And that's something we've certainly talked about, and of course we'd be really interested in partnering with anybody in the audience, anybody in the state of Indiana, really industry at large, in tackling some of these broader issues.
Great question, thank you. I have one last question for the panelists here. How can we work with Purdue to merge metrology materials and model-based techniques? You know, if you're a company, what are some of the ways that we could work together?
Mike, do you want to take that one first?
Well, you start and then I'll jump in.
Okay. Well, I think there are a few different ways to work with Purdue on this. One is through faculty and their particular research efforts. Another is connected to that is through INMAC. You know, we have an infrastructure and connectivity amongst ourselves to be able to address questions, concerns, challenges, and be able to help with those sorts of things. Mike, go ahead.
Yeah, I would say as faculty at large, we try and solve interesting problems, but relevant problems. And that's the key, is relevant problems. So having closer communications with folks in industry, knowing, really having our finger on the pulse of knowing what the issues are, helps us make sure that what we're doing is relevant. There's a second aspect of this is really the technology transfer. As academics, we love to solve hard problems. We love to build frameworks. We love to build tools. But really, the impact of our work is in making the world a better place. And that really comes from the transfer of this technology to the people who would actually use it. And that's really industry here. So please reach out to us. I mean, there's a reason our contact information is up here. You see Nate, mine, and also Mike Ursum's contact information here through email. And you can always email us and we can kick off a conversation that way.
Great. Well, thank you so much, Professor Sangid. Thank you, Professor Hartman. Really interesting discussion today. And thank you all participants all across the state, the country, and some abroad. Thanks for listening to us today. We hope to hear from folks again next week. We hope that you can consider participating with us next Wednesday. And with that, we will conclude.
Okay, thanks everybody. Have a good
Thank you, everyone.